Hello, everyone. I'm Mohamed Shalan. I'm associate professor at the American University in Cairo. Also, I'm an engineer who spent several years of his career working in the domains of digital ASIC design, EDA, and embedded hardware and software. So today I'm going to talk to you about OpenLane. Eventually, there are like lots of the things I'm gonna cover. Eventually, intersects with the first two talks. So I'm gonna go over them so quick, and also I'm gonna try to make it short because eventually there is a hands-on session which will start maybe like an hour from now. Which eventually covers like OpenLane in lots of details and show you basically how can we utilize OpenLane to do designs that can be integrated into curved chip and can be fabricated using either Chip Ignite or OpenMBW shuttles. As Mohammed and before Mohammed, Yuan mentioned, eventually there are like three ASIC enablers. So we need to have the design that we want to implement, and typically we do this at the RTL level using some hardware description language, typically Verilog. To accelerate things, we might be using IPs as well. And then we need the EDA tools, and eventually in order to produce something that can be manufactured, fabricated, we need the PDK. And eventually, at the moment, we are living in the age of being able to do to have all of these as open source. Especially after the release of the first open source PDK, the Sky 130 from Skywater, which eventually, as mentioned earlier, basically is followed by another open PDK from Global Foundry, basically for 180 nanometer, and then another one from Skywater, basically for 90 nanometer. So in order to understand how can we do ASIC design, eventually need to go back in history to see basically what's happened, because actually history will tell us basically or explain what we have in the present. So in early days of IC design, and this is typically before 1978. And eventually that time basically was referred to as the age of gods. And actually this term was coined by the famous Alberto Sangiovanni Vincentelli, when he addressed the Design Automation Conference in 2003 with his outstanding types of EDA talk. So basically at that point of time before 1978, and actually this specific year eventually for a reason which basically will be clear shortly, IC design and fabrication eventually went basically shoulder to shoulder. So eventually the people who did the design actually were tightly coupled with the people who were doing fabrication. So eventually when you want to design and fabricate chip, eventually we have the single team doing basically these together. And companies like Fairchild, Intel, Texas Instruments, eventually they were there at that point of time doing IC design, and eventually they operated this way. And back then we had very primitive tools to do design. So most of the designs actually were done by hand, as you can see in the picture, utilizing very simple tools like K-maps and others. And eventually we didn't have any kind of automation basically to help accelerating the design process, because basically we are dealing with the small number of transistors per chip compared to what we have today. At 1978, exactly something happened, and eventually that was work done by both Lane Conway and Carver Mead, where basically they introduce an idea of separating the fabrication from the design. And to do that, they pioneered what we refer to as the lambda-based rules. Probably if you had like a VLSI course at school, eventually you might have heard of this term. Where basically they came up basically with a system where you can do design And this design can be retargeted to any fabrication process. And eventually the people who will be doing the design eventually are basically, they need to know nothing about basically the fabrication, or they know a little bit about fabrication, and all they need to basically to get from the fabrication people is the process design kit, or the PDK. And based on their work, eventually they published one of the first VLSI text books, which basically introduction to VLSI systems. And eventually they offered the first VLSI course at MIT in 1978. Eventually, from that point of time, we refer basically to this age as basically the age of heroes. And heroes here basically refers to both Lincoln Way and Carver Mead, and eventually the co-founders of early ADA companies like Metro Graphics, Valid Logic Systems, Daisy Systems. And not only that, also the heroes also include TSMC, which basically was the world's first dedicated merchant foundry, which basically was opened the doors in like 1987. So basically, after that, basically we witnessed the age of men, according to Alberto, where basically we have tens of EDA companies, eventually including Synopsys and Cadence, and these companies eventually they are offering basically EDA tools, and these EDA tools eventually they are getting sophisticated with time, trying to cope with Moore's law, that eventually says basically the number of transistors double basically every like 18 to 24 months. So eventually we need basically these companies, they need to produce electronic design automation tools to enable the designers to cope with basically this rapid change in the number of transistors per chip. And eventually, in order to achieve this, what they basically what they did, eventually they started to borrow software development methodologies when it comes to abstraction, basically design reuse, in order basically to accelerate the design and try basically to cope with Moore's law. Basically following the software design process, which as most of you are already familiar with, eventually we have the coding step, where basically you do coding and maybe testing, and once you have basically a code, you give it to the compiler, and the compiler compiles it into machine code. Which actually it's this process, if we compare it to the ASIC process, basically is simple and way easier, because eventually when it comes to ASIC design or IC design, you eventually do similar steps to software, but when it comes really to converting the code that represents the algorithm that you want to implement, for example, in software using the compiler, here in IC design, it's a different story, because eventually you model your idea using HDL, hardware description language, and then eventually you take this HDL and convert it into something which can be used for fabrication. And then after fabrication, that takes a large number of steps at the foundry, and takes a long time. Eventually you're going to get the chip. So it's not like you push button and that we have in software, where basically push the button, you get the executable binary maybe after like few seconds, and worst case maybe minutes. It's really like big projects. But now actually we need to basically generate something that can be used for fabrication, and then wait for fabrication, and then we'll have the chip eventually can do validations and testing. So eventually, and not only that, it's longer, it's more complex. The implementation step, which eventually takes the hardware description language model of what we want to build and convert that into something that can be manufactured. And this thing basically is layout. And this layout basically will be used to to cut or print the mass that will be used in fabrication. And eventually, this step eventually that we're referring to as the implementation involves actually lots of steps, and these basically just sample of the steps that you might need to do in order to take the design from HDL model, typically at the RTL level, and then eventually convert it into GDS2, which basically is a format used to represent the masks layout. So ASIC implementation eventually requires lots of knowledge about what you are building, the functionality that you want to build, about how the chips functions, how they are fabricated, because eventually when the layout is generated, the layout basically has to be manufacturable, which means that it has basically to honor manufacturing rules, etc. So eventually you need to, as ASIC designer, you need to be aware of that, and also in many cases that you need to be aware of how the tools actually are working and functions, because eventually most of the EDA tools used in ASIC implementation, they offer like tens of options, and eventually you won't be able to understand these options or switches unless you understand how these tools eventually work and what kind of algorithm being implemented by these tools, which typically means that in order to do a successful IC design, you need to have like a large, diverse team, basically of engineers working together eventually to have basic successful IC design. So, and here basically I'm showing you just like a very simple basically view about basically the flow of steps that needed to do that. And here I'm just showing basically the major steps, not showing everything. So because eventually there are like way more than what basically I'm presenting here in order basically to have successful ASIC implementation. So typically when you start basically with the RTL, which basically the model of what you want to build in HDL, you pass it to the synthesizer, which gets the standard cell library, which basically a library of basically ready-made components like flip-flops, multiplexers, simple gates that eventually can be used to basically to realize your model as a circuit. Plus also some constraints that you can specify to the synthesis tool, like for example, I want this circuit to run at this particular frequency, or I want basically the circuit to have basically this amount, or to use this amount of silicon area, etc. So these basically considered as constraints that can be provided to the synthesis tool, and the synthesis tool eventually generates a circuit that matches the functionality of the model that you provide to the synthesis tool. And eventually this basically circuit will be represented also using hardware description language, because hardware description language eventually they allow basically like the representation of hardware at different level abstractions, including behavior, structure, data flow, and so on. Okay, once we have this, basically comes the step of floor planning, and eventually, depending on whether you are doing this for just a small block in bigger design or doing it for the whole chip. So the floor planning basically will be different based on what you are doing exactly. So for example, if I have a chip that has, for example, like a SysMod chip that has multiple blocks inside, that we typically refer to these blocks as macros, like CPU, flash controller, input-output devices, SRAM, and I/O pads. Eventually, we refer to this basically as the floor plan of the chip. And eventually, each one of these macros, eventually by itself has to be floor planned as well. But the floor planning of a macro will be different, because eventually the floor plan basically for a macro defines what's the area of silicon that basically will host the circuit, the components of the circuit that basically implements the functionality of this macro. And typically these components will be placed basically on virtual rows. Because these components, they are regular in basically in shape, so typically they are rectangles basically with fixed height. So they are basically placed on rows like these virtual rows, and part of the floor planning also is to specify where are the inputs and outputs or the pins. Also, during this step, we can do the power planning, and power planning eventually we create the power distribution network, and the idea here is to deliver the power supply to all components of your circuit, eventually with basically having the minimum IR drop, because eventually, and this IR drop, basic minimum IR drop, means that if you supply your circuit with, for example, with the 5 volt, you want basically every component in your circuit basically to get 5 volts, and not to get like 4.5 or 4.6 or eventually you want it basically to be 5 volt, basically as close to 5 volt as possible. And this is basically by creating a power distribution network that has very low resistivity, basically to deliver the current from the supply to different components. And not only that, it has to be rigid enough eventually to handle high current demands when there is basically current surges, basically because of activities happening in the circuits. After that, eventually we take basically the circuit, or what we refer to as the netlist, eventually made out of the components, eventually will be placed on the virtual rows in the floor plan of the macro that I showed earlier. And eventually, to do this, typically this is done in 2 steps. One of them is called the global placement, where basically the optimal location of each cell will be found, but these locations not necessarily basically like legal. So that's why it's typically followed by like detailed placement legalization, in order basically to legalize and basically place these basically cells basically in legal locations. And when I say legal location for a cell, eventually is when the cell basically is placed on a row and aligned by these vertical lines that we refer to them basically as sites. So they have basically start at specific sites. Basically, and then basically, and the cell is designed in a way that it's what basically will be basically the multiple number of the row sites. After that, basically comes the clock tree synthesis, where basically the clock distribution network is synthesized, and the main objective here is to deliver the clock basically in a good shape to all the components that needs clocking, like flip-flops and latches, and basically with minimum skew. Okay. And eventually to create, basically to do this, there are like several ways for doing that. We can create like tree, as the name basically suggests, because this is clock tree synthesis. Sometimes basically we can create the clock distribution network as a mesh, which typically use basically to minimize the skew. But in many cases, really, we don't really basically like care a lot about the skew, as long as the design does not have any timing violation and the clock is delivered to all clocked elements in a good shape. After that, we start to implement the wires that connect the components together, and this is the routing. And the routing basically is the most time-consuming step in this process. And eventually the routing is done using the available metal layers. Like for example, when like earlier, Yuan showed you for Sky 130, they are like 5 metal layers and 1 local interconnect layer, and these eventually are the routing layers. So eventually we use these layers to create wires and connect between wires and basically wire segments at different metal layers or routing layers using vias. And eventually the tool, which the router does that, eventually consumes lots of processing power eventually to achieve a successful implementation of all the wires that connects different design components. And because it's a complex process, also it's done in 2 steps, global routing followed by detailed routing. Once we are done with the routing, now we have the layout of for basically that can be used to cut the masks needed for fabrication. But before doing that, eventually you need to do lots of verifications. And these verifications basically are done within the step that we refer to as sign-off, and that this includes physical verifications like design rules checking, layout versus schematic or LVS, electrical rules checking, like for example, to make sure that basically like you didn't do anything wrong. For example, like you have, for example, an analog circuit, and this analog circuit eventually output is basically by mistake is buffered using a digital buffer. So these are kind of things that electrical rule checker would catch for you. And also we need to make sure that all of the clocked elements in your design eventually they are they don't basically have any timing violations, and this is typically done using the static timing analysis. Okay, so once you do these sign-off steps, and basically every one of these basically steps, sign-off steps, eventually they show you that you have a good layout for the design that you started with. Eventually, now we are ready, we're almost ready basically to submit design for fabrication. So eventually, in order to execute this flow of steps, we need basically like large number of tools, and eventually we need to, these tools can exchange basically different kind of data between them. And eventually, not only that, also like a methodology has to be defined to address different aspects of the ASIC design process. So typically what we do, we code this methodology basically and create what we refer to as a flow. And the flow eventually is nothing but set of scripts that automates the implementation process. When Sky 130 came out, and eventually we wanted to create or demonstrate that we can use open source EDA tools and open source designs and open source PDK to create open everything like chips. We needed to have to define a flow, and basically we decided to make this flow is open source as well. So basically everything will be open source. And eventually like this activity resulted in the OpenLane ASIC flow, which started as a flow for open everything tape out experiment, and this experiment eventually resulted in the fabrication of 6 system chips that are basically around one of the RISC-V CPUs. And basically with different configuration, different features, as you can see, and basically all of them eventually were implemented or realized using the OpenLane flow. So OpenLane eventually is an open source ASIC flow, which can be used with open source, which uses open source EDA, and can be used with open source PDKs, for whether it's Sky 130, 90, or GF 180. At the moment, basically we have support for Sky 130. Very soon, the GF 180 support will come out very soon, and then once it's basically that the Sky 90 is about to be released, eventually OpenLane basically will be ready for that, will support it as well. So OpenLane goals eventually is to have a push button flow, and the reason behind that is basically to bridge the gap between software engineering and hardware engineering, because as Yuan presented, we have basically more software engineers compared to hardware engineers. So we want basically to have like a path for software engineers basically to do hardware as well, and eventually OpenLane basically is targeting this idea, and basically we wanted basically to be the GCC for silicon. And eventually it's not only that, even we want basically to lower the bar, so that's basically not only engineers, maybe students, not necessarily at the level of like university students, maybe students at the level of high schools eventually, or even hobbyists that without even any engineering background eventually can do ASIC designs, and can make a good use of the Google OpenMPW free shuttles. And eventually, if they can do something very exciting that has a market, eventually they can target other shuttle programs like Chip Ignite. So OpenLane actually, since its release back in July 2020, which became very popular. And at the moment, they are like around like 270 clones every day. And out of these 270 clones, eventually it's around like 100, 120 clones are unique clones, which means basically 120 new clones every day, which means like new designers or basically users of OpenLane are coming every day basically and cloning them. But in total we have like around 250 every days, including newcomers and existing users. Currently it has almost 700 stars and almost 250 forks. So in OpenLane, eventually we put lots of emphasis on tool qualifications, tool calibrations, and addressing like missing tools. And eventually, when we started, we basically we built OpenLane to use the Open Road EDA tool chain. And eventually, back then, eventually it wasn't that mature, and eventually we had to basically to work with the Open Road team, basically to share with them the problems and basically and work together eventually like to enhance things. Basically over these 2 years, eventually there are lots of development in both basically OpenLane flow and the Open Road application, which is the main EDA tool used inside OpenLane. And because of that, basically lots of things that we used to use, basically they are not in use at the moment. And the way we use OpenLanes can be used by the designers or users eventually makes this abstracted. So eventually all the designer, all he or she needs basically to provide is just basically the design files, like for example, RTL Verilog, and basic set of configuration parameters basically to tell the flow basically what to be done. And today, eventually we're going to learn about basically all of that. However, OpenLane takes care of everything. A good designer must basically be on top of everything, so must be aware of what's happening. So OpenLane, while running, it generates lots of log files, lots of reports. So a good designer should go and check these log files and reports for for problems, for warnings. And a good designer will never basically let warning basically be in his or her logs without understanding the meaning and basically and the reason behind that. So even though that we're trying to simplify things and make it basically easier for anyone to do ASIC design, eventually as you are gaining more experience, eventually you need basically to pay attention to lots of things. At the moment, there are lots of effort happening at the OpenLane side, eventually to raise the bar when it comes to quality of experience. So eventually we are doing lots of development now, eventually to automatically identify errors and basically explain them and present them to the designer basically in more meaningful way compared basically to what you would see basically in the log files or in the reports. So till basically we have this fully nailed down, eventually as designer, eventually you have basically to go and basically check for all of these things. Just a warning before I finish this talk, ASIC design is complex, and however OpenLane tries to simplify things. OpenLane represents basically a part of the design process, because there are other things that have to be done, including design verifications, which involve basically like function verifications at the RTL and Git level. Through simulations and test benching, and not only that, also timing simulation needed for dynamic timing analysis. Also, these basically they represent basically like a big chunk of the design process, and eventually like good amount of time, probably like 50% or maybe sometimes more, basically of the actual effort to design something eventually will be spent in verifications. And verifications in ASIC design is similar to testing in software. So as testing, basically a good software project basically will involve lots of testing activities that typically consume maybe 42 to maybe sometimes up to 60, depends on the type of the project. So it's the same story here. Verification basically equivalent to testing, and eventually it basically consumes lots of effort and, as well. So to just get you started, here are basically like basic steps. So I'm not gonna go over them because eventually they will be discussed in details later today. But if you want to get started with OpenLane, immediately just point your browser to openlane.io. So yeah, that's it.